Good afternoon, everyone. Welcome to my Ph.D. defense talk. Today, I'm going to talk about efficient, reliable communication in the short blocklength regime through list decoding and through feedback. So depending on the availability and types of feedback, there are three major cases when we communicate over a channel. So channels without feedback, channels with full noiseless feedback, and channels with finite stop feedback. So each case corresponds to a section in today's talk. And finally, I'm going to summarize my talk. Okay, so my first research project is mainly motivated by the ultra-reliable low-latency communication in 5G or URLLC. So URLLC is mainly for delay-sensitive services such as autonomous driving, tactile internet, telesurgery, factory automation, so on and so forth. So this figure shows you the block error rate versus end-to-end latency for some practical applications. And we first see that different applications may have different set of requirements. But for 5G URLLC, we are mainly interested in the region where the block error rate is no greater than 10 to the negative 5. And meanwhile, the end-to-end latency is no greater than 1 millisecond. So on this plot, we are looking at this purple dot. So achieving both the ultra reliability and low latency is a very challenging task. And a crucial step is to design very powerful short blocklength code. Okay, so 5G URLLC is now made possible thanks to the advances in finite blocklength information theory. This is a field that studies the fundamental limits of communication at short blocklength. So to start with, let n denote the block length, capital M denotes the message size, epsilon star denotes the error probability for the best fixed length codes of block length n and message size m. So in 2010, Polyansky presented an upper bound on epsilon star known as random coding unit bound. And then meanwhile, in the same paper, Polyansky also gave a lower bound on epsilon star called meta-converse bound. So together, these two bounds characterizes the error probability region for the best fixed length codes of block length n and message size m. Okay, so I grabbed this plot from Koskin et al.'s survey paper published in 2019. The region delimited by the RCU bound and the meta-converse bound is shown in the light blue region. And also, I need to mention that this plot is mainly for n equal to 128, k equal to 64, and we are looking at the binary input additive white Gaussian noise channel. So in short, BI AWGN channel. So on this plot, the author also examined a couple of contemporary short blocklength codes. So we can see they look at the tail biting convolutional codes with different number of memory elements. They also look at non-binary LGBC code, binary LGBC code, and CRC80 polar code. So among all these codes, we see that the best one is given by this m equal to 14 tail biting convolutional code. So on this plot, it corresponds to the red dashed line with the little squares. So if you look closely, then the performance at a low SNR even outperforms the RCU bound. And then as SNR increases, then its performance gradually deviates away from the RCU bound. Okay, so we know that this code has a remarkable performance already. However, the problem of using this code is that it has high decoding complexity because the number of states will be exponential in the number of memory elements. So that means that what we really care about here is, can we approach the RCU bound at a reasonable complexity? And that is a focus on my first journal paper. So in our paper, we propose using the CRC80 convolutional codes under serial list Viterbi decoding as a good solution. Okay, so first let's briefly talk about the serial list Viterbi decoding process. So let's assume that we are transmitting the all zero code word, and let's assume that this is what we received after the AWGN channel. Then serial list Viterbi decoding is an extension of the classical Viterbi decoding algorithm, which produces a rank order list of code words. So in practice, then we will first specify a quantity called maximum list size, and in our work, it's called capital psi. So let's assume that psi is equal to 1, then it means that we are only allowed to do one traceback. And in this example, we see that the first traceback does not pass the CRC. So then the serial list Viterbi decoder is going to output a negative acknowledgement, or in short, neg. And meanwhile, we also call the list rank at which the decoder stops the terminating list rank, and denoted by this capital L. So in this example, L is equal to 1. Then let's suppose that now our maximum list size psi is at least 2. Then in this particular case, we can do one more traceback. And luckily, the second traceback indeed passes the CRC. But we see that the second traceback is still not the all zero path, meaning that we now have an undetected error. And in this example, then L is equal to 2. Okay, so now we understand the SLVD process. Now let's look at the system diagram. So consider a k-bit information sequence U. So we first do our CRC coding with the generator polynomial P of x to generate a k plus m bits code word. Then the code word V is taken as the input to another rate 1 over omega convolutional encoder with new memory elements, which finally produces the code word C. Then using BPSK modulation, we can convert C into a real point X. Then we are going to transmit X over the AWGN channel. Then at the receiver side, once we receive a random point Y from the space, then we adopt the soft SLVD aided with the CRC P of X. Then the SLVD will either give you a k-bit estimate U hat, or it simply gives up and outputs a neg. And then to analyze such a system, we are going to define two important linear block codes. So if we think of V as a free information sequence, then V to C can be thought of as a higher rate code CH with minimum distance daemon H. Then similarly, the code from U to C can be thought of as a lower rate code CL with minimum distance daemon L. Okay, so we are also interested in two concatenated codes here. So depending on whether we are using a zero terminated convolutional codes or two biting convolutional codes, the resulting concatenated code is called a CRC ZTCC or CRC TBCC. Okay, so now I'm going to introduce another very interesting quantity called supremum list rank lambda. So we know that the maximum list size psi is just an integer, and one can set it arbitrarily large. However, we are working with a finite code, meaning we only have finitely many code words. Then this implies that there exists a threshold on psi beyond which the decoder will always be able to identify a path that can pass the CRC. And we call such minimum threshold the supremum list rank. So in other words, the supremum list rank is the inherent maximum list inherent maximum value for the terminating list rank psi. Sorry, terminating list rank L. Okay, so we can. Oh. How about this? Okay. Okay, sorry about that. So we can easily imagine that a worst case scenario is to put all the lower rate code words to the bottom of the decoding list. This will create an upper bound on the supremum list rank lambda. So the upper bound is simply the size of the higher rate code minus the size of the lower rate code then plus 1. Okay, so and in practice, we can identify some examples where lambda achieves this trivial upper bound. However, it still remains an open problem how to determine lambda exactly for a given CL and CH. So the bottom line here is the terminating list rank L is always a random variable ranging from 1 to the minimum between lambda and psi. Okay, so going back to our work, we are mainly interested in addressing the following two problems. Problem 1, given a convolutional code, how to design the optimal CRC generator polynomial. And problem 2, what is the performance complexity trade-off for the resulting concatenated code? So now let's discuss the first problem. So the first problem can be formulated as follows. So for given ZTCC or TBCC, CRC degree M and SNR, then we wish to minimize the error probability over all possible degree M CRC generator polynomials. So I want to emphasize that here we assume the maximum list size psi is lambda, so that we either have correct decoding or we have undetected error. Okay, so by looking at this minimization problem, the first obstacle we face is P comma lambda does not have an analytical expression, let alone talking about how to minimize it. So as a good workaround, then we can consider the unit bound of P comma lambda as our objective function. So in coding theory, once we know the distance spectrum for the lower rate code, call it C daemon L all the way to Cn, then we can easily write out this unit bound on P comma lambda. So that means instead of minimizing P comma lambda, we try to minimize the upper bound on P comma lambda. And we call the solution as the distance spectrum optimal CRC polynomial, or in short, DSO CRC polynomial. Okay, but so now the problem has been simplified, but it's still very computationally extensive because for each CRC generator polynomial, one needs to calculate the full distance spectrum, which is still very difficult when the block length is large. So can we further simplify this proxy minimization problem? And it turns out, yes, we can. So for sufficiently large SNR, then this minimization problem can be further simplified to maximizing daemon L. Okay, so now we really have a tractable problem because we don't have to care about the full distance spectrum. Okay, so the next question we want to answer is, can we come up with an upper bound on the objective function daemon L? And theorem 4 answers this question. So here we fix a CRC degree M and a higher rate distance spectrum B daemon H all the way to Bn. Then we are going to look at the smallest output Hamming weight at which we just accumulated 2 to the m code words. And we call that distance W star. And then theorem 4 says daemon L will be upper bounded by 2 W star. Okay, so this theorem is really convenient because it means that if we look at the output Hamming weight from daemon H all the way to 2 W star, then we are guaranteed to identify this unique degree M DSO CRC polynomial. Okay, so now let's briefly talk about the DSO CRC search algorithm at high SNR. So this problem is first considered by Low et al. In their 2015 journal paper, and they are mainly looking at the ZTCC case. So Low et al.'s algorithm is a two-phase algorithm where the first step is to collect all the zero-terminated convolutional codes of trellis length capital N and output Hamming distance bounded by d tilde. And once we have this data set, then by specifying the CRC degree M, then Low et al. Was able to identify the target CRC polynomial. However, if we directly apply his algorithm to the TVCC case, then we are going to immediately realize that the algorithm becomes very inefficient. And the main reason is because we have enormous number of catastrophic till biting paths that start and end at the non-zero state and then spend most of the time in the all zero state. So we want to avoid that. Then to remedy the situation, we propose another algorithm which has 3 steps. So the first step is to collect the so-called non-catastrophic irreducible error events with output Hamming weight bounded by d tilde. And then once we specify the target trellis length capital N, then we can use all these irreducible error events to reconstruct all the till biting convolutional codes with trellis length N and output distance bounded by d tilde. And finally, we can find our DSO CRC polynomial. Okay, so as a result, then for k equal to 64 and some well-known rate 1/2 ZTCC, we were able to identify the DSO CRC polynomials for those ZTCCs. And then this table simply summarizes the DSO CRC polynomials for the TVCC counterpart. Okay, so now let's talk about the performance of CRC-aided convolutional codes under SLBD. So the performance measures includes the probability of correct decoding, probability of undetected error, and probability of NAC. And we want to understand how these quantities vary with maximum list size psi and SNR. Okay, so theorem 5 answers the question when SNR is fixed. So when SNR is fixed, then PC comma psi and P comma psi are both strictly increasing in psi and will converge to PC comma lambda and P comma lambda respectively, where the sum of the two quantities is equal to 1. So the implication of this result is that if one wishes to minimize the total failure rate defined by P comma psi plus P nec comma psi, then the minimum value is simply equal to P comma lambda. And the optimum maximum list size psi star must be at least lambda. Okay, so that means that for any P comma psi, it suffices to consider its boundary P comma 1 and P comma lambda. And now we wish to understand how these boundaries vary as a function of SNR. So let's suppose that we know the higher rate distance spectrum denoted by the B values and the lower rate distance spectrum denoted by the C values. Then for P comma 1, we are going to use the nearest neighbor approximation to approximate P comma 1. Then for P comma lambda, instead, we are going to use this truncated union bound to approximate P comma lambda. And then for P nec comma 1, then we are going to use the difference between the truncated union bound and the nearest neighbor approximation to approximate P nec comma 1. And then this example is simply to show you that our approximation will become tighter as SNR increases. Okay, so now let's turn to another quantity called expected terminating list rank. The reason we care about this quantity is because the average complexity of SLVD will be governed by the expected terminating list rank. So we wish to understand how it varies with SNR. So it's straightforward to see that as SNR increases, then this expectation will uniformly convert to 1. Then the real question we want to answer here is what happens if SNR approaches 0? So theorem 6 addresses this question, and it says in the limit of SNR going to 0, then the expected terminating list rank will converge to expected number of L, given that we are transmitting the origin point. Okay, so in general, this quantity is still very difficult to calculate analytically, but using a very simple random coding argument, one can show that there exists possibly nonlinear lower rate code CL with convergent expected terminating list rank upper bounded by 2 to the m. Okay, so that answers the question when SNR goes to 0. Then the real interesting question is, can we approximate the expected list rank at any SNR point? And then it turns out we can use this very useful parametric approximation to do it. So let's assume that we can obtain the convergent expected list rank and call it L bar. And let's assume that at the operating SNR of interest, then we can obtain its error probability P comma lambda. Then our strategy here is to use this simple convex combination to approximate the actual expected list rank. So this approximation turns out to be very accurate in practice. So we are going to see that soon. And then the other significance of this result is that it can be seen as a bridge that connects the complexity of SLVD with the performance of SLVD. And more importantly, if we look at the CRC ZTCC, then very often we are going to notice that L bar is roughly to the m. And then suppose we wish to achieve a target error probability P star, then to maintain a small expected list size, let's say no greater than 2, then 11 imply that it's sufficient to consider m roughly less or equal to negative log P star. Okay, so this plot shows you the expected terminating list rank versus SNR. So we first, so this example is mainly for CRC ZTCC, and here we first see that the expected list rank will convert to 1 as SNR increases, and when SNR goes to negative infinity, then the expected list rank is roughly to the m. And we also see that our parametric approximation works fantastically well because it almost matches all the simulated points. So the implication of this plot is that if we focus on the high SNR region, then it means that the expected list rank is roughly 1. meaning that the total complexity of SLVD is just the complexity of standard Viterbi. Okay, so finally, we derive the empirical complexity formula for SLVD, and this total complexity comprises 3 terms. So the first term, CSSV, measures the complexity for a single standard Viterbi, and C-trace measures the complexity for doing additional traceback during SLVD, and C-list measures the complexity for maintaining a sorted list during SLVD. And I want to emphasize here that the C-trace will be governed by the expected list rank. Okay, so finally, let's look at the performance complexity trade-off. So the first plot is for the CRC ZTCC being studied in our paper. So the y-axis represents a gap, SNR gap to the RCU bound. And so the smaller the gap, the better the code performance. And the x-axis represents the complexity of SLVD. And the parameter setup is we are looking at transmitting 64 information bits, and the target error probability is 10 to the negative 4. So on this plot, each marker corresponds to a fixed ZTCC. So let's say that now we look at this blue cross, so that that means we are looking at a fixed 1317. Then all the points from the top to the bottom corresponds to DSO CRC polynomials of degree 3 all the way to 10. Okay, so
you can use the cursor to show people where that little.
Oh yes, yes.
Not use the one on the computer so that people in Zoom can see.
Oh sure.
Yeah, there you go.
Okay, so I'm gonna use this now. Okay, so the first observation we make here is as we increase the CRC size, then the resulting CRC ZTCC performance gets improved dramatically, and we see the same pattern holds for all the ZTCCs being studied here. And the minimum gap achievable here is this point, which is roughly 0.4.
Can you comment as the performance, the gap to the RCU bound is dropping quickly for a given convolutional code? What happens to the complexity?
Yeah. Oh, yeah. That's a good point. So so we see that from the plots. Then as the performance gets better, then the complexity nearly remains the same. Okay. Okay. So horizontally, if we fix the n plus mu, which means if we fix a fixed amount of redundancy, then this plot suggests that it's better to consider a large CRC code used with a smaller ZTCC to achieve the similar performance while maintaining a low complexity. Okay, so what about the CRC TBCC? So first, immediately we see the exciting results that some CRC TBCC further closes the gap. So we see that some points reaches near 0 gap, and some points even achieve a negative gap, meaning that those CRC TBCCs actually outperform the RCU bound at 10 to the negative 4. Okay, and we also see that the same pattern holds for the CRC TBCC case. So that means that eventually the CRC TBCC was indeed able to achieve the RCU bound at a reasonable complexity.
Hengjie, I have a question regarding complexity. What do you mean exactly by complexity?
So here the complexity means the total number of operations by decoding a code word. And we are calculating the complexity using our empirical formula.
Okay.
Okay.
We have a question from President.
Explain the significance of the RCU bound given that some pure plots are below the bound. How do we explain that, and then what is included with the value of the bound?
You mean the gap to the RCU bound?
Yeah, but you're below the gap.
So why can you be below the RCU bound?
Yeah.
I think that's a very good question. So first we see that if we only focus on the TBCC code only, then the TBCC code itself is enough to achieve the RCU bound. And the reason is because we don't have the zero termination overhead.
President Dolachek is asking not specifically about the TBC codes, but is it a theoretical error to exceed the RCU bound, or is that an acceptable? Would you expect that some code could exceed it?
Oh, yes. That's because the RCU bound is simply a random coding unibound. It doesn't mean that it's only a bound for the random code, but it doesn't say anything about the performance of the actual short blocks encode.
Well, okay, is it a converse, you know, I think you need to talk about like the meta converse, achievable versus converse.
Sorry, I'm still not following the question.
So is the RCU bound, so, it's a bound on something. Is it a limit on the SNR that can you perform at an SNR lower than the SNR that the RCU bound provides, and why?
So the RCU bound says if you look at a fixed SNR, then what's the upper bound on the error probability for the best fixed length codes? And then here our simulation suggests that CRC TVCC can achieve the target error probability with a smaller SNR, meaning that if we look at the same SNR, then its error probability must be less than RCU bound.
Right. So why don't you take us back to the very first plot you showed us way back at the beginning of
Sure.
the slide.
This one?
That plot, yeah. So you've got the RCU bound and the meta-converse bound and the blue region here. What does it mean?
So it means that if we look at any particular SNR point, then the best error, the error probability for the best fixed length codes must be bounded, must be upper bounded by the RCU and must be lower bounded by meta converse.
Okay, so is it okay if you perform to the left of the RCU bound?
That's right, yes.
Okay. So why is, why is one, okay. So you can obviously do worse than the RCU bound, but you can do better than it too, but you can never do better than that.
That's right, yeah. Yeah, you can never do better than the meta converse bound.
Okay.
Then what is the significance of the RCU bound if you can be on both sides?
Sorry, I'm not following the question.
So what does it mean? So I think Professor Belichick is saying, well, if I can do better than it, then what does it mean?
Oh, it means that the code performance is good enough, and then we wish to. So the main question we want to address here is whether we can identify codes that can beat the RCU bound while maintaining a low decoding complexity.
So what kind of a code do we know can achieve the RCU bound?
TBCC.
But I mean, what is the word? What are the three words?
Random code.
Right.
Yeah.
So there is a code that can do that well. If I'm not doing that well, I should try harder.
Yes.
But
Would it not be fair to say that this is what a random code would do, and you're trying to construct a deterministic code that has some other desirable properties that could also do better than the random code?
Yes. Yeah.
okay. So,
Thank
but you can't. So we don't know that we can. We know we can do at least as well as the RCU bound. Can we actually build a system that does that?
So I guess I got confused because the plot was focused majorly on being above that bound.
Most codes are above the bound. So I guess lots of other papers before us, that's all they did because nobody ever expected to break through that.
Okay.
So, but now we're actually, that's why we start plotting the meta-converse. Now we think about the whole banana, both sides of the peel, because we're in the banana. But before Hengjie, nothing was in the banana. So that's why it's interesting to oh, well, whatever.
Okay. Okay, so now let me turn to the second part. Okay, so now let's move on to talk about the channels with full noiseless feedback.
Before going to that, can you show the previous plot of gap? Yeah.
Yeah.
Do you have a plot that shows gap to normal approximation versus complexity?
No, I don't have it in this slides. So we never did a gap to normal approximation because normal approximation will not be accurate when we look at this particular block length. So we mainly focus on the RCU bound.
So you think that normal approximation is not good for achievability of the performance? I mean, you can do better than that.
Yeah, I guess Hengjie doesn't know about this, but we did, in work we're doing with Jacob, we have, because Bill Ryan likes to plot the normal approximation too, but it just makes us look even better in kind of an artificial way, because at short block lengths, the normal approximation is not as good as you can actually get with the RC band. For as soon as the block length's like around 500 or 1,000, it's great, but around where we're working and around 100 bits, it's not quite right. Oh, he may not, Darish may not have heard.
Yeah.
Oh, Darish, can you hear us?
Yeah, and another thing, you never found maximum likelihood decoding performance of concatenated CRC and convolutional code, right? You said that it's very hard to find that.
You mean the best CRC TBCC?
Yeah, but you did, you optimized CRC in order to get maximum minimum distance of overall code.
Yes, yes.
But how about the performance? You said that performance is very difficult to obtain, right? Concatenated. CRC with inner convolutional code, find the maximum likelihood decoding performance for this concatenated code.
So we are indeed looking at the maximum likelihood decoding of the CRC TBCC, because here we are assuming the maximum list size is large enough so that we either have correct decoding or undetected error. So that's equivalent to ML decoding.
Okay.
Mm-hmm.
So this entire work here is very nice, but it has focused on CRC convolutional codes. Do you have any thoughts? Can this be applied to some other class of codes in some modified fashion? Like if you're looking at short block lengths, like non-binary PC codes or something like that?
Yes, that's a good question. So I do think that we can try to extend this framework to other inner linear block code. For example, we can look at maybe some BCH codes or RS codes. But I think the major difficulty here is we must be able to efficiently identify the daemon L of that quantity. Yeah. So for convolutional code, it's rather easy because you can just do Viterbi search and then you can easily identify the daemon L. But for some other codes, maybe we don't have trellis, so it means getting the minimum distance becomes harder.
Do you want to mention the work you've been doing with Jacob?
Yeah, so currently I'm working with Jacob on the finding the CRC for the longer information length, say like K equal to 128. And what we realize is once K gets large enough, then we were unable to achieve the RCU bound.
I guess I meant the other. I mean, so we're already looking at having an interpolar code.
Yeah.
Oh yeah, that one. Yeah.
Yeah.
Yeah. So in our recent paper, we compare the CRC-80 polar and CRC-80 convolutional codes, and it turns out that the at short blocking regime, then CRC used with TBCC is still better than CRC used with polar.
Actually, if you're interested in that, Jacob we're presenting it at ICC today, and he's going to be giving his.
ICC today?
Yeah.
But you're presenting it remotely.
Yeah. Right. Yeah. Yeah.
Okay.
So yeah, but it's on ICC. I don't know if anybody else is registered for that, but you can see the talk.
Okay. Is there any other question? Okay, so let's talk about the second one. Okay, so the second talk will be based on my 2020 ISIT paper and my recently accepted IT transaction paper. So the well-known bad news delivered by Shannon himself is that feedback does not improve the capacity of a memoryless channel, but still we know that feedback can offer a lot of benefits. For example, in the context of variable length transmission, then it has been known that feedback can simplify coding schemes. For example, the famous Hornstein scheme for the binary symmetric channel and its later extension called posterior matching. Feedback can also achieve better error exponents. For example, Bernard showed that the best error exponents for the variable length feedback over the GMC can be determined exactly given by this formula. Feedback can also achieve universality. For example, the famous fountain code for the erasure channel. And also feedback can improve the first order and second order coding rates as evidenced by Polyansky's work in 2011. Then in the context of fixed length transmission, we also know that feedback can achieve better error exponents. For example, the well-known Shao-Kuai-Keller scheme for the AWGN channel. And feedback is recently showed that it can also improve the second order coding rates for compound dispersion discrete memories channel. And this is proven by Aaron Wagner in 2020. Okay, so this plot shows the system diagram for a memories channel with full noiseless feedback link. So in order to use such a channel, then we first need to specify variable length feedback code. So let's take a look at the code definition. So the first component of the code is that we must have a common codebook available both as the encoder and the decoder. And thanks to the full feedback, this codebook can even be designed on the fly. Okay, so the second component is a sequence of encoding functions, which determines the transmitted symbol X key as a function of the codebook U, transmitted message theta, and the current channel observations up to time t-1. And the third component is a sequence of decoding functions, which provide the best estimate of theta at time t. And it's a function of the codebook U and the current channel observation. Okay, finally, we also need a stopping time tau, which is a function of the filtration generated by the codebook U and the current channel observation. In other words, once we know the current channel observation, then the decoder can decide whether to stop or not. And then at stopping time, the decoder is going to apply the decoding function so that we can get our estimate theta hat for the transmitted message. For tau itself, it has to satisfy both the average block length constraint upper bounded by L, and the actual error probability must be upper bounded by epsilon. Okay, so that's how we define the VLF code. Then in general, our goal is to determine the minimum average block length for any VLF code. Then in this talk, we are mainly going to focus on the DIC, and we are going to discuss a very interesting coding scheme called small enough difference coding scheme. So this scheme is first introduced by Nashvar et al. In their 2012 information theory workshop paper. And this scheme mainly works for the symmetric binary input channels. So let's take a look. So the first step is we need to introduce a concept called belief state vector, bold letter rho of t. So this vector is a rho vector where the rho I of t is simply the posterior probability of theta equal to I. And then by default, we assume that before transmission, all the posterior probabilities are simply uniform. Then we know that this belief state vector can be easily updated using the Bayes rule. Okay, so now let's look at Nashvar et al.'s SED bipartition. So first, let's define S0 and S1 be two subsets for the entire message set. And then we also define pi0 and pi1 as the probabilities contained in S0 and S1. Then the SED bipartition says at time t+1, upon obtaining the belief state vector, we need to partition the message side into S0 and S1 such that the probability difference must remain non-negative. And at the same time, the difference cannot be too large. So it has to be upper bounded by the minimum posterior in S0. So that's why it's called small enough. Okay, so the SED bipartition essentially defines the common code book at the encoder and the decoder. And once we know SED bipartition, the encoding is really simple. So if the transmitted theta is in S0, just transmit 0, otherwise transmit 1. And then a straightforward implementation of SED bipartition would take complexity k times 2 to the k, assuming the message size is 2 to the k. And Antonini et al. In 2020 further reduced the complexity to k squared by considering a type-based algorithm for the relaxed SED bipartition. Okay, then what about the decoder? So for the decoder, upon receiving the new channel observation YT+1, then the decoder can update the belief state vector, and then the decoder is going to adopt the following stopping time tell, which is a minimum time at which we first observe a posterior probability that exceeds the threshold 1 minus epsilon. And then the decoding function is simply the message index with the maximum posterior probability. Okay, so we can easily check that such a selection of stopping time meets the error probability requirements. Okay, so the first major question we want to understand is, why is this SED coding rule interesting? So to answer this question, we first need to look at the quantity called log likelihood ratio. So we define the log likelihood ratio for each message index j. And once we do that, then Nashra et al. In their paper showed the following interesting result. So they said for symmetric binary input channels, the SED bipartition yields a two-stage submartingale for UI, assuming that I is a transmitting message. Then more specifically, if you have a negative log likelihood ratio, then the average step size is lower bounded by capacity. And once you have a non-negative log likelihood ratio, then your average step size is exactly equal to a quantity called C1, where C1 is defined in 23. And at every time instant, the absolute step size is upper bounded by C2, where C2 is defined in 24. Okay, so this result is very useful because once we know this two-stage martingale, and we can apply the Dup's optional stopping theorem, that will lead to a upper bound on the average block length. So in their subsequent journal paper published in 2015, they said the VLF code constructed from the SED coding rule satisfy the following upper bound. And also worth mentioning here is Polyansky's result for the variable length stall feedback code. So I want to emphasize that for stall feedback codes, then the stall feedback symbol is only used to terminate the transmission, and the encoder itself cannot use stall feedback symbol to generate the next transmitted symbol. So Polyansky showed the following upper bound on the VLSF code. So why do we mention the two results together? It's because even with full feedback, Nashra et al.'s result is still much looser than Polyansky's, which is a situation should not happen, right? Because Polyansky is looking at limited use of feedback. How come its result can be even better than the best use of feedback, right? So to further illustrate this problem, so let's consider a BSC with capacity 1/2 and with target error probability 0.1%. So if you plug in the numbers in Nashra et al.'s bound, then this is what you get. You have a very large constant term. However, if you plug in the numbers in Polyansky's bound, then you have a very small constant. Okay, so this is to illustrate the looseness of Nashra et al.'s result. Then for us, our goal is to seek a new upper bound for the SED coding rule that's better than Polyansky's bound. So eventually, this is our main result. So we obtain a refined achievability found for the VLF code constructed from the SED coding scheme. And the result looks rather complicated because we now have a very complicated constant term. However, if you plot our results, then for example, still look at the same BSC and the same epsilon, we see that our results denoted by this solid blue curve becomes better than Polyansky's VLF achievability bound. So that means we were able to achieve our goal. We also simulated the actual performance of the SED coding scheme, and we noted that there's still significant room for improvement. Okay, so that concludes the discussion for the BIC. Now the next question is, can we generalize this very nice SED coding scheme to the binary asymmetric channel? So let me first talk about the definition of binary asymmetric channel. So such a channel is specified by two crossover probabilities. So P0 is a probability for flipping a 0 to 1, and P1 is a probability for flipping a 1 to 0. And then for BAC, there are two special cases. The first one is called a regularized BAC, which requires P0 must be upper bounded by must be bounded between 0 and 1/2, and P1 must be bounded between P0 and 1 minus P0. Then the second special case is a BIC. So why do we mention the regularized BAC here? It's because every BAC can be transformed into an equivalent regularized BAC by either flipping the outputs or flipping the inputs. Okay, so that means it suffices to look at the regularized BAC, right? And if we want to generalize the SE decoding rule, then the first step is we want to resort to some useful facts. So fact one, consider any BAC by defining a constant term called Z. We know its capacity exactly. And we also know its capacity achieving input distribution exactly. More importantly, we were able to show that for any regularized BAC, pi1 star is always less or equal to pi0 star. And this is important in our generalized SE decoding rule. Then the other useful fact is that for regularized BAC, C1 is equal to the key-out divergence between the conditional output distribution given transmitting a 1 and the conditional distribution given transmitting a 0. So this means if we want to achieve the C1 quantity, eventually we have to send in 1 all the time. Okay, so now let's review our final answer. What's the generalized SE decoding rule? So intuitively speaking, if we want to achieve capacity, then posterior matching principle says we need to make sure that pi0, pi1 distribution is roughly the capacity achieving input distribution. And one way to do that is the following. So let's first identify the message index that corresponds to the current maximum posterior probability. So there are two cases. If none of the messages has a posterior that's larger than pi1 star, then we are going to partition the message set into S0 and S1 such that pi0 over pi0 star minus pi1 over pi1 star is bounded. Okay, so that's why it's still called small enough. And then once we have a posterior that's greater than pi1 star, then we are going to exclusively assign the message index ahead to S1 and then the remaining message to S0. So still, the generalized SED bipartition defines the common code book. So the encoder and decoder will be exactly the same as in the BIC case. Okay, so the first question we want to understand is, why is this generalized SED decoding rule interesting? That's because with the generalized SED decoding rule, we can still preserve the same two-stage submartingale as shown in the BIC case. Okay, so once we have, so that addresses the first question. Second question is the generalized SED decoding scheme always achievable, right? Because if you cannot do this at any particular time, why do we even consider it? And the theorem 12 answers this question affirmatively. It says if we consider this particular objective function as a function of the subset S0, then once we identify the optimal S0, then the resulting bipartition will satisfy our generalized SED decoding rule, meaning that you can always achieve our requirement. Okay, so finally, with the two-stage submartingale and also by applying a variant of Dub's optional stopping theorem, we were able to show the following upper bound on the average block length for the VLF code. So let's take a look at how it performs. So we look at two cases. The first case is still the same BIC example. We see, so here the dashed line represents our general achievability bound for the BAC. So we see that it still outperforms Poliansky, but it is worse than our refined achievability bound for the BIC. And then for the BAC, so we look at this particular BAC with capacity 1/2. We still see that our bound is still better than Poliansky's. Okay, so that concludes my talk for the channels with full noiseless feedback. Now let's turn our attention to binary input channels with finite stop feedback. So this talk will be based on my most recent ISIT paper and my upcoming IT transaction paper. Okay, so first, let's look at the system diagram for a memories channel with stop feedback. So as I said earlier, stop feedback symbol is only used to terminate the transmission, and the encoder cannot use stop feedback symbol to generate the next transmitted symbol. And so, and also we have an additional requirement that we only have M stop feedback actions. Okay, so the first step is we want to still define a variable length stop feedback code for such a channel. So more specifically, let's consider M decoding opportunities N1 all the way to N sub M. And let's consider a particular message size M, target error probability epsilon. We wish to specify such a code. And then likewise, the first component is we need a common codebook available both at encoder and decoder. But for now, this codebook must be designed and fixed before transmission. Then the second component is we need a sequence of encoding functions to generate the transmitted symbol. But the distinction is now X key can only depend on the codebook and the transmitted message. And the third component is we need a sequence of decoding functions, which provides the best estimate of theta. But now the time must be confined in the set N1, N2, all the way to N sub M. And then we also need to define a stopping time tau. Now tau can only take values in set N1 all the way to N sub M. And tau must be a function of the filtration generated by the codebook and the current channel observation. Then similarly, at stopping time, the decoder is going to apply the decoding function to produce the final estimate theta hat. And for tau itself, it also needs to satisfy the average block length requirement and also the error probability requirement. Okay, so the general goal is to determine the minimum average block length for an arbitrary VLSF code. Okay, so in our analysis, we are going to extensively use a quantity called information density, which is a quantity popularized by Polyansky in his 2010 paper. So this is a definition of information density. Then if the input distribution can be written as a product of PXI and the channel is memoryless, then we can decompose any length and information density as a sum of random variables. Then if P sub X is the capacity achieving input distribution, then it turns out that the expectation of the information density is equal to channel capacity, and the variance of the information density is equal to channel dispersion. And in our work, we are going to assume IID inputs are distributed as capacity achieving input distribution. Okay. So here I'm going to recall recent non-symptotic achievability bound proven by Yavas et al. So Yavas showed the following non-symptotic achievability bound for the VLSF code for the Gaussian channel under the peak power constraint. And here, by a slight modification, his result is directly applicable to any memoryless channel. So more specifically, 44 gave an upper bound on the average block length, and 45 gave an upper bound on the error probability. So our strategy is that we are going to use his result to motivate an integer program. So we are going to consider the upper bound on L as an objective function, and we are going to further constrain the upper bound on epsilon star by epsilon. Okay. So more specifically, our first step is to relax the probability of the unit events to the marginal probability. So then we define the objective function capital N. We also define the feasible region, which includes all the decoding times such that the minimum gap must be at least 1, and the error probability must be satisfied. And then eventually we have the following integer program. So for a fixed gamma, then we wish to minimize over all possible decoding times subject to all decoding times is in feasible region, and all decoding times must be integers. Okay, and finally, by performing the following two-step minimization, we can identify the globally minimum upper bound n star. Okay, so this is very nice, but the first obstacle we face is how can we evaluate this length n? How can we evaluate this tail probability for length n information density? Okay, so let's first discuss that question for the BI-AWGN channel case. So for BI-AWGN channel, the per letter information density is continuous, and the length n information density can be written as a sum of IID random variables. So it is straightforward to think about the central limit theorem, right? Because if we consider the standardized sum, then central limit theorem says standard sum Sn will converge in distribution to a standard normal random variable. So then Wang et al. In 2017 considered a Gaussian model that applies the CLT. And it said for n sufficiently large, we are going to use the Q function to estimate the tail probability. However, our question is, what if n is small? Okay, so to as its primary contribution, we are going to resort to a powerful tool called Edgeworth expansion. So Edgeworth expansion says, suppose we have n IID absolutely continuous random variable with zero mean, variance sigma square, and suppose we also know the cumulants for each w, then if we satisfy this regularity condition, then the CDF for Sn can be written as the CDF of a standard normal plus the PDF of a standard normal times the summation n to the j minus 2 times a polynomial called pj comma x, where this polynomial requires the cumulant kappa 3 all the way to kappa j plus 2. And then this is a very useful expansion because we see that the error term is always upper bounded by little o of n to the negative s over 2 once we truncate the bound to the previous s terms. Okay, so this turns out to be very useful. So let's directly apply it and see what happens. Okay, so this picture shows you the tail probability versus block length for the following particular BI-AWGN channel. And we see here that when n is relatively large, say greater than 20, then we tried order 5 Edgeworth here, and we see that it performs remarkably well. Okay, so its performance almost match every simulated point. However, the problem is once n is really small, like less than 15, then we see this oscillation issue around the zeros. So especially you see some values even becomes negative. So that means order 5 Edgeworth for small n is still not good enough. So we need to fix this problem. And then to remedy this situation, then we resort to another very powerful tool called Petrov expansion. So Petrov expansion says, suppose we still have n IID random variables with zero mean, variance sigma squared, and suppose we still know the cumulants, then in a moderate deviation regime, then Petrov can write the CDF of Sn into the following particular expansion. So in this particular expansion, there is a quantity called capital lambda, which is the Kramer series. So this is very difficult to figure out. However, in Petrov's book, then he presented the following order 3 Kramer series, which can be written as a function of the cumulants of W. So in our work, for our purposes, we are mainly gonna apply the order 3 Petrov expansion. Okay, so as a result, then our strategy is for n greater than some threshold n star, then we apply the order 5 Edgeworth. When n is less than n star, then we are gonna apply the order 3 Petrov. And here n star is the threshold at which two expansions are equal with a common value less than 1/2. Okay, so let's take a look at how the result performs. Okay, so on this plot, the blue curve represents the performance of the order 3 Petrov. So we see that when n is relatively large, then the order 3 Petrov is not as good as order 5 Edgeworth. However, when n is small, then we see that the blue curve becomes much better than the Edgeworth because we don't have the oscillation issue. So our strategy is if we combine the two expansions together, then the resulting approximation will be really tight. Okay, so the green curve shows you what happens when we combine them together. So it almost matches every simulated till probability. Okay, so that addresses the question of computing the till probability. Now let's return to the integer program. So the integer program is still very challenging to solve. So instead, we look at the relaxed program by allowing real value decoding times. And then it gives the following program. And it turns out for such a program, we can analytically solve the optimal real value decoding times. So this result is easily obtained by applying the KDT condition in convex optimization. So 58 gives the optimal NM star, and 59 gives the recursive relation between two consecutive decoding times. So due to this special structure, we call this as the gap constraint sequential differential optimization procedure, or in short, SDO. Okay, so finally, we have all the tools necessary to evaluate the achievability bound. So here, this is a plot that shows the rate versus average block length by applying the two-step minimization and gap constraint SDO. So we see that when M is small, when M goes from 1 to 2, then the achievability bound is dramatically improved. And then as M further increases, then the benefit is diminishing. And when M reaches 16, then our achievability bound is almost approaches Polyansky's bound. So this says Polyansky's VLF achievability bound can be approached with a small number of decoding times. Okay, so that concludes the discussion for the BIWGN. What about BIC? So for the BIC, the per letter information density is a lattice random variable. And then in terms of the till probability, then the till probability for any length n information density can be solved exactly using the binomial CDF. Then let's take a quick look at the till probability versus block length, and we see this. So we see that now the till probability is not a monotonically increasing function. It has this zigzag behavior. So on this plot, we identify all the local maximum values. And then the question is this phenomenon universal? And it turns out, yes, indeed, it's universal. So we can show that if we define a quantity called alpha I in this particular way, then when n is alpha I minus 1, then we have the increasing part. And then when n is in between alpha I and alpha I plus 1 minus 1, we have the decreasing part, which show that we always have the zigzag behavior. And due to this behavior, then alpha I is called the local maximizer. Okay, so that's not a good news, but we were able to obtain the following useful results. So we were able to show that if the number of decoding times m is less than nm star, then we can show that the optimal decoding times for minimizing the upper bound must be among the set of local maximizers. Okay, so that's a useful result because that greatly reduces our search space. Then the next question is, it's a discrete case. How can we figure out the optimal decoding time? And it turns out that we can develop a similar procedure called discrete SDO procedure. So if we define the G minus function and G plus function for N1 in this particular way, and then for any pair Ni comma Ni minus 1, where I is at least 2 in this particular way, and let's assume that when the maximizer or minimizer is empty, then G minus is negative infinity and G plus is positive infinity. Then discrete SDO is given by the following sequence of inequalities. So it says the optimal integer value decoding times for the original integer program must satisfy that the following inequalities. So if you look at the format, it means if we specify a particular N1, then we know the range for the N2 star. And then condition on N1 and N2, we know the range for N3 star. So that means essentially the discrete SDO procedure is a first step search. Okay. So as a result, it's possible that you can have a collection of decoding times that simultaneously meet all these requirements. And then we can figure out the unique optimal decoding times that can yield the minimum upper bound. Okay, so now we have all the tools. We just apply the two-step minimization and the discrete SVO to the BIC. So we again obtain a similar achievability bound for the BIC. So again, we see all the pattern that hold for the BIWGN also hold for the BIC. And again, we confirm that when M is equal to 16, then we can approach Polyansky's bound. Okay, so that concludes my talk to the third part. Then let me summarize my talk. So case one, BIWGN with no feedback. For such a case, we designed a new code called CRC80 convolutional code. And simulations show that several CRC TVCC under SLVD outperform the RCU bound at reasonable complexity. Then in the second case, we show that for BIC and BAC, we further refine the non-symptotic VLF achievability bound so that they eventually outperform Polyansky's VLSF achievability bound. And in the third case, we consider the binary input channels with finite stall feedback. And then for this case, we developed two methods to evaluate the VLSF achievability bound. And for both BIWGN and BIC, we confirm that Polyansky's bound can be approached with a small number of decoding times. Okay, so finally, I would like to thank my significant collaborators in the past 5 years, Ethan Liang, Minghao Pan, Linfang Wang, and Rajab Yavas from Caltech. And I would also like to thank my advisor, Professor Rick Wessel, for all the support and guidance in the past 5 years. I would like to thank my committee members, Professor Laura Dolachek, Christina Fraiguli, Alex Sherstov, and Darish Divsala for serving on my doctoral committee. I would like to thank all faculty members of the ECE department and the mathematical department for all the wonderful graduate courses, which lay a solid foundation on my research. I would also like to thank my friends in California, Weinan Song, Linfang Wang, Bijie Bai, Yun Liao, Minghao Pan, and many others for all the wonderful times we have spent together. And finally, I would like to thank the National Science Foundation and Qualcomm for the funding support for my research. So that concludes my talk, and thanks for your attention.